Okay, so let's start this. Today we are going through tutorial 7. This is basically the first question of tutorial 7. I'll just write it down here. This is tutorial 7. Okay, so basically now what I'm going to do is, because these are just the last two sessions that we're going to cover. So what I'm going to do is, I will go through this, basically the questions of tutorial 7 I'll go through, and later, I'll also take up some extra questions so that you have some basic practice of what kind of questions can come in the exam, and you have uh, some solving capability basically. So I will take up some extra questions beyond your tutorials. Okay. So first, let's go through the tutorial, and then I'll take up the extra ones. Just a moment. Okay. So let's begin. The first question is the table that shows entropy versus energy of a system of identical charges stuck to the labeled corners of a tetrahedron is. So this was basically a problem covered in one of the lectures of professor, that the idea was that you have some shape, some regular three-dimensional object, and at the corners of which you are placing identical charges, right? So the idea was to, whatever the shape is, so depending on the number of charges and the shape, suppose I have, say, a cube. That's the example that's her took in class. So suppose I have two charges in a cube, then there could be many ways possible in which I can place those charges. So suppose for a given interaction potential energy U, for just two charges, I will have the placement kind of fixed. That suppose my interaction energy is just E square by A, where A is the distance, basically the side length. Then I know that the two charges are placed on adjacent corners only. But even this can be done in many ways. Firstly, I can choose one corner of the cube, and then there are at least three adjacent corners among which I can choose, right? If I'm correct, yes. I have three at least adjacent corners. So even then, I have many arrangements possible. So this is what we are trying to do. What we'll do is, uh, first, we'll talk about, for different number of particles, the different potential energies which are possible, and corresponding to each potential energy, how many possible arrangements can be done in the given object. That will give us entropy, right? So this is pretty straightforward actually. In the case of tetrahedron particularly, it is very straightforward. So okay, so what is a tetrahedron exactly? Tetrahedron is, I have a shape of this form. I have a triangle, and this is inside this point which I have marked. It's inside the plane of this sheet. So basically, I am joining these sides like this. So the idea is, what is a tetrahedron? Tetrahedron is basically, maybe if I take the side view of this object, this is like the bottom view of this object. If I take the side view, this is the point which I have drawn here. This is the point which I am drawing. It would have, yes. So this is a tetrahedron. What do we have here is basically four equilateral triangles as the sides of the tetrahedron. So this is one equilateral triangle, this is two, the bottom is three, and the one behind is four. This is the fourth one. So we have four equilateral triangles as its faces. Since these are equilateral triangles, what we know is that each side will be of the same length, right? Suppose this side length is A, then even this is A, this is A, this is A, this is A, and this length is A. All of these lengths are A. So now let's begin. Let's begin trying to find different configurations. For just one charge, there is no interaction energy, so it does not make sense. For suppose I have one charge here, which means U is equal to zero. The interaction potential energy is practically zero. In that case, you would think that I can place this charge on any of the four corners. So I do have four different kinds of possibilities. But with one charge, all the four corners are also identical, right? Hmm, okay, no, wait. If the corners are labeled, okay, here I just remember that they have spoken about labeled corners. Ah, so in that case, I think that even those four corners, one single charge being placed on any of these four corners would give four possible arrangements. Uh, okay, let's think about the other cases. Suppose let's start with two charges. Suppose I have two charges and I have placed them in these corners. Let's name the corners actually. That would make more sense. This is A, this is B, this is C, this is D. So I'm placing two charges, one on A and one on B. So in that case, uh, what do I have? The potential energy that I get is E square by A. And if you see, uh, I for any kind of arrangement which will have two charges, the potential energy is going to be this only in the case of a tetrahedron. In the case of a cube, you could have just for two charges also you could have different arrangements where the potential energy would be different. But in the case of a tetrahedron, you have just for two charges you have only one potential energy possible, which is E square by A. So in that case, what are the number of arrangements possible? The number of arrangements would simply be uh, 4C2 because I have four corners and I have to choose any two, right? So that gives me 4C2 is equal to 4 into 3 divided by 2, which is 6. So this is my number of microstates or number of possibilities, which is 6. So entropy is simply log of 6. So for E square by A, I have log of 6 as the entropy. For E square by A, this is my U. I have S is equal to log of 6. For U is equal to, now I have basically considered all possible scenarios when there are only two charges. For two charges, I have considered all possible scenarios, right? Because this is the only kind of scenario that can happen. So now let's consider three charges. So if I'm taking three charges, in that case, what do I have? The potential energy is E square by A because of charge at A and B. That's the interaction between A and B, plus E square by A, that's the interaction energy between B and C, plus E square by A, that's the interaction energy between A and C. This is AC, this is BC, this is AB. The total interaction energy is 3E square by A in the case of three charges. And wherever we place these three charges, there is no different potential energy possible. Only this potential energy will happen. So in a way here, in this particular case, a given value of U is also associated with the number of charges present. In the case of cube, that was not the case. For the number of charges being same, say n equal to 2, I could have many different U's. But here, if we fix U, the number of charges are also being fixed. So when U is equal to 3 square by A, which means that n is equal to 3, in this case, what are the number of possibilities? What are the possibilities here? Uh, the possibilities are simple. I am just, I am occupying three corners. Basically, I am leaving only one corner empty. So I can choose that corner also. Or maybe I can choose three corners where I place. Either way works. I can choose one corner which is empty, or I can choose the three corners where I put in charges. So it's either 4C3, wherein I choose three corners where I'm putting in charges, or I choose one corner where I don't put in charge. That is 4C1 is equal to 4. These are the possibilities. So S is equal to simply log of 4. So for U is equal to 3 square by A, S is equal to log 4. And now when all four corners are occupied with charges. In that case, I have U is equal to simply E square by A, AB, BC, CD, AD, AC, BD. So there will be all these combinations. Uh, E square by A from AB, E square by A from AC, E square by A from AD, E square by A from BC and BD, and E square by A from CD. So this is also in a way 4C2 into E square by A is equal to 6 E square by A, but the microstates or possibilities are just one. So S is equal to 0. So we have the answer right here. We have E square by A corresponding to log 6, 3 E square by A corresponding to log 4, and 6 E square by A corresponding to 0. Yes. So this is the option, right? Only this first one, uh, the labeled corners part is somehow a little bit confusing for me because if they're labeled, they're distinct corners. But of course, no. Okay, okay. So if the labeled corners we're talking about is distinct corners, in that case, I would have to multiply 4C2 by 2 factorial also, even in these other scenarios. So here we are considering if symmetry is not being broken, then we are considering the corners as identical only. Otherwise, these scenarios won't be possible. So this is the answer. This is the answer. This option is the correct answer. Okay, let's go to the next one. Okay, here it is. So here the question is find the average of the square of the angular momentum in the harmonic trap problem discussed in the video tutorial 2. Assume that omega points in the z direction and do it for a single particle. Okay, we're doing it for a single particle firstly. Average of this and the average of the square of the angular momentum. Okay, so firstly, what is the Hamiltonian in this case? Hamiltonian comes out to be p square by 2m, because there's a harmonic trap as well. So there is also kappa by 2 into x square. Uh, this is pi square, xi square, half kx square, right? And you also have a term of this form, omega dot l. But now it's given that omega is in z direction only, corresponding to omega z. Okay, so in that case, I will only have Lz, which is which will act. So what is the value of what is the expression for Lz in terms of these operators? It's xpy minus ypx, right? Basically, this is simply r cross p, and I want only the z. I want only the z component of this. So that's what this is: xpy minus ypx. All right. Uh, so yeah, this is what I want. And what has been asked is that we want uh, the Lz square is expectation value. That is what we want to calculate. So this is expectation value of xpy minus ypx whole square is equal to x square py square plus y square px square equals to x py y x. The average of this is what we want to calculate, right? So how do we calculate an average of this form? All right. So to do this, okay, let me check the question again. And the average of the square of the angular momentum of the harmonic trap. Right. So yeah, this has to be it. Okay. So now let's see that omega points in the z direction. So I suppose it has to be Lz square. Okay. Mm, so to calculate this average, what do we do is uh, I will have mm, what we do is we simply e raised to power minus beta h into Lz square integral over dq e dqx divided by minus beta h dqe dqx. This is what will give me average of Lz square, right? This is what we have been doing uh, since, like, this is just the weighing factor and Lz square. Uh, this with the weight divided by z. This is just the denominator is just z, the partition function. This is what gives me the average value of any quantity, right? This is what we. This is how we evaluate average for any quantity. So exactly that's what I've written. Just the quantity that we require weighted by this factor integrating over all the degrees of freedom divided by z, which is just e power minus beta h integrate over all degrees of freedom. Okay, so this is what has been done in the class as well. Sir has done a similar problem, and this is the approach that he's followed. So we'll also follow this or follow similar approach. In that case, what we end up with is I have x square p y square plus y square p x square minus 2x py y px, this multiplied by, this is my Lz square multiplied by e raised to power minus beta h, uh, minus beta, and the h is basically this whole Hamiltonian is h minus beta pi square by 2m into e raised to power minus beta kappa by 2xi square into e raised to power beta omega into xpy minus ypx. That's it, right? Omega dot L, omega z is omega basically, omega into xpy minus ypx into beta, beta into omega into xpy minus ypx. This is the expression that we have. This integrate over dqp dqx, this whole divided by just e raised to power minus beta h dqp dqx. This is just a little bit tedious calculation. There is no difficulty as such in this. All you have to do is carry out the tedious calculation. So let's do this part. Let's evaluate the first term only for time being. Integrated x square e y square e raised to power minus beta. When I'm saying pi square, by the way, okay, so when I should have marked the vectors here, right? This is vector. Um, I meant pi square is basically px square plus py square plus pz square, and I is not a particle index here, which generally we were using because we are not taking in particles. We have to evaluate it for a single particle only. So we're not taking in particles. So there is no summation over particles here. So this is just beta p x square. Actually, I'll take only beta py square here. Py square by 2m. There is beta px square, pz square also, but here what I require for the integration is only py square. So those I'll take out separately. E raised to power minus beta kappa x square by 2 is for beta omega x py. This dx dpy. This is the this is one part of the integral multiplied by is to minus beta px square plus pz square by 2m e raised to power minus beta kappa by 2 y square plus z square plus e raised to power beta omega minus beta omega y px. This thing multiplied by dy dz dpx dpz. Okay, so now again, even within the first term, I am first evaluating only this. This is what I'm evaluating because here I have a prefactor which I have to take care of. So that is why I have to be careful evaluating this. So x square e power minus kappa x square by 2 e power beta omega xpy dx multiplied by I have py square e raised to power minus beta py square by 2m dpy. So first I'm evaluating only the x part, and this part I'm keeping separately. Okay, so this part I'm keeping it as some I which I have to evaluate eventually. Yeah, so evaluating only this part for now, what I get is x square is for minus beta kappa by 2 x square minus the beta has been taken out 2 omega py by kappa x is what I have inside. Hmm. So to complete the squares here, into py square minus beta py square by 2m dpy into I. Now to complete the squares here, I'll require the an additional term which is x square e raised to power minus beta kappa by 2 x square minus 2 omega py by kappa x plus omega square py square by kappa square. This inside, so this is I have to basically multiply and divide by this term. So this term, what does it come out to be? Minus of minus beta kappa by 2 into omega square py square by kappa square. Basically a minus sign because I have multiplied inside, now I'm trying to divide it. So that's what gives this minus sign here. Hmm, kappa kappa gets cancelled. Okay, and then I have dx and multiplied by py square e raised to power minus beta py square by 2m dpy into I. Okay, so this is integral x square e raised to power minus beta kappa by 2 x minus omega py by kappa the whole square, right? Multiplied by this constant e raised to power beta omega square py square by 2 kappa into py square minus beta py square by 2m dpy into I. Alright, so now x minus omega py by kappa is a new variable. X minus omega py by kappa is, say, some alpha. I don't know. There is a dx also somewhere which I missed out. Dx. So dx is just equal to d alpha. So dx basically does not change, but my x now is different. So alpha plus omega py by kappa the whole square e raised to power minus beta kappa by 2 into alpha square d alpha for beta omega square py square by 2 kappa py square minus beta py square by 2m dpy into I. This is what we are left with. So now alpha square e raised to power minus beta kappa by 2 alpha square uh, plus omega square py square by kappa square e power minus beta kappa by 2 alpha square plus 2 alpha omega py by kappa e power minus beta kappa alpha square by 2 d alpha multiplied by e raised to power beta omega square py square by 2 kappa py square e raised to power minus beta py square by 2m dpy into I. I'm writing down all the constants because then otherwise sometimes what happens is you forget a term or two and then the whole calculation you have to keep on searching where did you miss out the term or something. So it's better to take some more time and write down each and every term rather than miss out on something. So now integral of alpha square. I'm now talking about individual terms here. Integral of alpha square e raised to power minus beta kappa by 2 alpha square d alpha. What is the range of alpha? So we haven't talked about the range yet, but because dx dy dz basically will take x going from minus infinity to infinity and even momenta in each direction going from minus infinity to infinity. So this is just simply uh, so x is going from minus infinity to infinity. Similarly, alpha will also go from minus infinity to infinity. So this integration has limit from minus infinity to infinity. So this is like the derivative of Gaussian function that you must remember. Uh, so we basically have e raised to power minus some constant c alpha square d alpha is equal to root of pi by c, right? This is what we get. So integral of alpha square e raised to power minus c alpha square d alpha is equal to simply do del by del c with a negative sign of integral e power minus c alpha square d alpha. If I do this, I will get exactly this, right? If I do this derivative, the derivative that I have pointed out on the right hand side, this derivative, if I take this derivative, because C is not a variable dependent on alpha, so I can just take this derivative inside, and when I perform this derivative, what I get is exactly the left hand side, right? So what I can do is I can simply say that this is also equivalent to del by del C of root pi by C, which gives me uh, C derivative. C is minus half, so with the minus sign, that minus gets cancelled, we only have half square root of pi by C cube now, because C is 3 by 2, C power 3 by 2, so C cube. So this is what you end up with. So this is your result here, and this is my first integral. So my first integral ends up being, here C is simply beta kappa by 2. So I'll directly write down the integrations now, the values of these. So the first term becomes 1 by 2 square root of pi divided by C cube, where C is beta cube kappa cube by 8. Beta kappa by 2 the whole cube. This is what I'll write for now. The first term I've written down. Now I'll write down the second term. So here there is no alpha involved in this part. There is no alpha. There is only omega square py square by kappa square. So this will simply give me square root of pi by alpha. So plus omega square py square by kappa square root of pi by alpha, pi by c, sorry, and c is beta kappa by 2. Okay, so this is what I end up with. There is an alpha square. I got an extra c. Okay. Hmm. And what about the third term now? The third term, this term has alpha as a linear power, and I said that alpha is going from minus infinity to infinity. So here we have alpha square, which is obviously an even function. So e power minus some constant into alpha square. This is an even function with respect to alpha. But here this linear power is odd in alpha. So in that case, an integral from minus infinity to infinity will give me 0. So this term contributes nothing. This gives me 0. So now the integrations have been performed. I have these two terms, and I have to write down this entire thing. So e raised to power beta omega square py square by 2 kappa, 2 kappa into py square into e raised to power minus beta py square by 2n into I. There is a dpy and into I. This is the remaining term. Um, okay, so simplifying this further and evaluating only for the first term right now. So 1 by 2, I'll take square root of pi outside. Actually, what I'll do is, let me take 2 pi divided by beta kappa whole square root outside. So then what I have here inside is, firstly I'll have a 1 by 2, uh, because beta kappa by 2 is gone, so you have into 2 by beta kappa. It was squared, but there is a square root, so the square and square root get cancelled. Plus omega square py square by kappa square into nothing. You will have nothing here, right? Yes, this is what it is. Okay, and here we have py square e to the power of minus beta uh, minus beta into 1 by 2m minus omega square py square by 2 kappa. Sorry, omega square by 2 kappa. Omega square by 2 kappa into py square. So minus beta py square by 2m. And the second term is plus beta omega square py square by 2 kappa. Yes, this is what we have into dpy into I. All right. So now this one is going to be much simpler than the previous case because 2 pi on beta kappa is just py square here, e raised to power minus beta into 1 by 2m minus omega square by 2 kappa into py square plus omega square by kappa square py to the power 4 just for minus beta 1 by 2m minus omega square by 2 kappa py square dpy into I. This is what you have. So again, this term, the dpy integration is pretty straightforward, just that my c, my constant term is different this time. So what I'll be getting is square root of 2 pi by beta kappa. This is just tedious calculation. I hope you will be able to follow what I've done, but you will have to follow along with your own pen and paper because otherwise you'll not be able to exactly get what I'm trying to do here. It will be just a lot of instruction. It will be like it's just algebra. There is nothing difficult about this. As in no conceptual thing. Algebra can be difficult sometimes, but there is no concept involved as such. Okay, so square root of pi again divided by c cube, but the c here is different this time. It's beta cube to 1 by 2m minus omega square by 2 kappa cube. This is what we have here. Yes. Uh, okay, there should have been 1 by 2 as well. There is a half also, right? In this expression, there is a half as well. Plus omega square by kappa square. Same thing, but this time for alpha power 4, we had seen till alpha square, right? Integral of alpha square e raised to power minus c alpha square d alpha was half square root of pi by c cube. Now further take one more derivative to this. If I take one more derivative by c with a negative sign, then what I end up with is alpha square e raised to power minus c alpha square d alpha is equal to integral alpha power 4 power minus c alpha square d alpha is equal to the same derivative here I'll be taking. So then what I'll get is um, minus 3 by 2 in multiplied. That will give me 3 by 4 uh, square root of pi upon c raised to power 5 this time. This is what I eventually end up getting. Okay. So the same thing has to be applied here. Omega square by k square. I will have a 3 by 4 as well. 3 omega square by 4 kappa square. And the integral gives me square root of pi divided by beta power 5 1 by 2m minus omega square by 2 kappa whole power 5 is the integral, and then there is I which remains. Okay. Uh, this is the first term and I'm yet to evaluate even I. Where is I here? Okay, so the entire term here I had called I. Hmm, I might get some terms here as well. Right. So what is going to happen is um, into I can keep it like this only. Why? I'll tell you. So eventually what we have to do is we have to divide the whole thing by z as well, which is the partition function, right? This whole thing has to be divided by z also. So in that case, this I will be cancelled out just like that. The I part can be separated. Only the remaining part, the dx and dpy part, I will have to evaluate in the z. The remaining part will be I, which will just cancel out from top and bottom. So I don't have to be concerned about it. So let's write what z would come out. Only the dx and dpy part of z. Okay. So z also would be um, e raised to power minus beta. I said py part I need 2 square by 2n minus kappa by 2 x square x and py part I require e raised to power omega beta omega. There is a beta here also. Forgetting beta omega x py, and there is a minus ypx which I don't care. That multiplied by I. Okay, this dx dpy into I. This is my z, right? So let's evaluate this. E raised to power minus beta py square by 2n beta kappa by 2 into x square minus beta is taken inside. I'm merging these two. 2 omega um, py by kappa into x is to power beta py square by 2n minus dx dpy. The same thing again. We have done this already. A power minus beta kappa by 2. Mm, just let me check this. I did get something similar only, right? Yes. Beta omega square py square by 2 kappa is what I had to take outside. Beta omega square. There was a 2 also somewhere. Was there? Omega square py square by 2 kappa. Beta into 2 kappa. Here I've taken this, you know what alpha is. Alpha is simply x minus omega py by kappa. Again, I've taken that only here. I've taken this term outside. 1 minus beta py square by 2m dx dpy. So here what I end up getting is square root of pi 2 pi by beta kappa into integral e raised to power minus beta 1 by 2m minus omega square by 2 kappa. This is something that I got here also. Yes, py square dpy. So this gives me square root of 2 pi by beta kappa multiplied by square root of pi by beta into 1 by 2m minus omega square by 2 kappa. This into I is my z. I hope I haven't made any mistakes here. Right. So let's see what kind of options are present. Yeah, I think I would get the answer, hopefully. Let's try it. So this is just the first term, by the way. The x square py square term is only what we evaluated yet. There are three more terms to go, but it will be very similar, so you don't have to go through the entire cycle again. It will just be, we can simply uh, see what the similarities are and get the answer directly. Okay, so yes, here is, this is the term which I have. I'll copy this, I'll put it here, paste, and now I'm dividing this by z, which is 2 pi by beta kappa into square root of pi by beta 1 by 2m minus omega square by 2 kappa. Yes, this is it. Okay, so what I do is I'll cancel out these. Obviously, I'll cancel out these root pi's. And what I get is, we're almost at the end, so I hope you're not losing out patience. 1 by 2 beta kappa into, okay, we can also cancel out betas, and what I'll get is just a beta square term common outside. There will be one beta and beta. Yeah, so I can just, okay, no, let me not do this right now. Okay, so what I can do is I can just cancel out this. This becomes square, this becomes power 4, and make this beta power 4. We're canceling this out. I can cancel this out, make this a square now, and make this a power 4. Yes, so now what I'm left with is just this beta into 1 by 2n minus omega square by 2 kappa plus 3 by 4 omega square by kappa square into beta square. Yes. Um, in the denominator, I have 1 by 2m minus omega square by 2 kappa, the whole square. So I'll have to somehow make this denominator is equal to evaluate this term. The I basically gets cancelled. There is an I also here which gets cancelled with this I. And this at least seems very sorted an expression, not much of a confusion. Okay. 1 by 2 beta kappa. I'll have 1 by 2m minus omega square by 2 kappa in the numerator. Okay, no, I'll have to be a little more carefully. Let's do this. This is beta square kappa. This is 2 beta square kappa, and this is 3 omega square upon 4 kappa square beta square. So I need a kappa and I need 2 kappa and this denominator both. So what I'll do is I'll multiply by 2 kappa into 1 by 2m minus omega square by 2 kappa plus 3 omega square divided by, yeah, I think this works, divided by 4 beta square kappa square into 1 by 2m minus omega square by 2 kappa the whole square. Yes, this is what I end up getting. All right. So now minus, let's see, kappa by m minus omega square is what I'm left with, plus 3 omega square, right? Minus plus 3 omega square divided by 4 beta square kappa square 1 by 2m minus omega square by 2 kappa the whole square. So what I have here is kappa by m plus 2 omega square divided by 4 beta square kappa square 1 by 2m minus omega square by 2 kappa the whole square. This is what I end up with. So this is just average of x square py square. But because of symmetry, you can say that y square px square will also be exactly this. Exactly this. So adding that, I can just make this 2 times. So x square py square plus y square px square average is just 2 times this entire value. What about you also have terms like minus 2 x py into y px. You also have this, right? But uh, that's what we saw that okay, no, it's not that simple. Wait, what is the kind of answer that we have here? Kappa pi m plus 2 omega square. Is that my answer? Kappa pi m plus 2 omega square. Here, what do we have? We have omega square minus or plus kappa by m. What do we have? Yeah, we do have, sorry, sure. We do have omega square minus kappa by m. I'll take 2 outside. Here this. And beta square also is there, which means t square is also there. So I kind of know the answer, but I have to check with this term also. So we will have to. There's no choice here. Um, this actually might contribute. For some reason, I had expected that this won't contribute, but this term might. Okay, so just let's check. Py, ypx, e raised to power minus beta. Just take one. I'll take only x first. X e raised to power minus beta. Um, py square does not matter. E raised to power minus beta. Kappa x square by 2 e raised to power plus beta x py. Right? Yes. Let's start with just the x part, x integral part. Let's see if uh, we do get some different contribution. We know that what we do with this is beta kappa by 2 x minus omega py. Omega kappa, what is it exactly? Omega py by kappa. Omega py by kappa, the whole square into e raised to power beta omega square py square by 2 kappa is something that comes outside, and you have an x here, dx. This is what we have here. All right. So um, this is alpha e raised to power minus c alpha square d alpha into this constant, which is e raised to power beta omega square py square by 2 kappa. Yes, that we cannot forget, obviously. Um, Plus omega py by kappa e raised to power minus c alpha square d alpha e raised to power beta omega square py square by 2 kappa. So this is already 0, but this isn't 0 right now. I do end up getting some contribution from this part, right? Mm, omega py by kappa to square root of pi by 2 pi by beta kappa. I was afraid of this. It is for beta omega square py square by 2 kappa, right? And I had py by px terms as well. So now when I multiply with the py term, which sits outside, this becomes py square. And I also have some e raised to power minus beta py square by 2m to dpy. So yeah, this does end up giving me some contribution. So omega py square by kappa square root of pi divided by um, what did we have? 1 by 2m minus omega square by 2 kappa. This the whole cube, because I had py square outside. So which is why I'll get this. And there will be a 1 by 2 as well. Omega by 2 kappa. Mm, so when I did x, okay, wait, when I did z, for z, what did I end up with? I see. So here only this term is coming out as a cubic term now. Uh, and when I do for ypx as well, this is what I'll end up with. Exactly same. Nothing new. Nothing old. Yeah. So this square, so dp, uh, dz and dpz are what remain, dz, dpz, and the terms corresponding to it. This is what I am calling I0 now. Some I0. Why? Because I don't want to be bothered with it. Even in the Z part, that will be isolated. So I need not bother about it. Um, and here in the Z part, what I get is, okay, why did I miss out on that? Square root of 2 pi by beta k is also there. Yeah, this whole square divided by what I'm getting is, yes, square root of 2 pi by beta kappa square root of pi divided by 1 by 2n minus omega square by 2 kappa, the whole square. This is what I get here. So this will go away, but here I'll be left with omega square by 4 kappa square. Root pi will also go away, but I'll have something like 1 by 2n minus omega square by 2 kappa, the whole square is the term which remains into I0, which gets cancelled here. So this is the third term which we have. The other two terms are already evaluated. Kappa by n plus 2 omega square. Is there a 4? Okay. It's beta square. I might have missed a beta somewhere. I'm sure I would have missed a beta. Because otherwise this won't be dimensionally similar, right? So I'm sure I have missed out on a beta here. Let me just take this term down. Yes. Kappa by n plus 2 omega square. And I have 4 beta square k square kappa square. Uh, where did I miss out on the beta? Something that I'll have to figure out. Where did I do that? Here in this case, there is a specific reason why beta square came in. Array, yeah, there is a beta cube here itself, which I missed out. Of course, there is a beta cube here itself, and there is a beta here. So I will have a beta square here, of course. And this is the term which we have here. By the way, this was minus 2, right? This had a minus 2 sign with it. So then what I end up with? Um, little confused now. I hope I've done the calculation correctly. I think I have, but I'm having a little bit of a doubt now. I have everything else correctly placed here. Just that with the omega square thing, Hmm. 4 beta square kappa square. Uh, and here also, if I'm not wrong, I do have that. Or maybe I should check whether I'm mistaken somewhere. This is right there. What gave me 2 here though? Acha, because of this half. Right. So the same half will come from the other side as well because of py square, right? Yeah. So that gives me 1 by 4. And what about these guys? Is there Acha, this was just x square py square. So when I added, I had 2 multiplied. So here my denominator is just 2, not 4. Right. So when I do this negative minus, I have to basically take a 2 here, take a 4 here. Okay, let me do this more systematically. There's a 2 omega square here, minus omega square divided by 4 kappa square beta square. There is a 2 here also. Yes. Hmm. Into divided by 1 by 2m minus omega square by 2 kappa, the whole square. So basically what I am getting as my answer is kappa by m plus omega square divided by 1 by 2m minus omega square by 2 kappa, the whole square. And here of course we have beta square kappa square, 4 beta square kappa square. This is my final answer that I'm getting. Hopefully I have not done any computational errors. But apparently none of the answers are matching here. Honestly, it will be very difficult for me to go back and check the entire thing where I have made a mistake. So I think the idea is clear how this is to be done, and this this is just some small calculation error, uh, some denominator numerator which I have missed out. So please check it for yourself and get this answer done. I think I have shown enough for you to understand how to do this. Uh, Third question is the Euler-Maclaurin formula is the approximate equivalence of this. This is the approximate equivalence. The summation is basically an integral plus the function at value 0 plus some r, which the remainder part is given by this expression. So what they're saying is choose some function f of x is equal to this. The value of alpha is greater than 0, which makes r equal to 1% of the approximate answer. Okay, so what they're saying is that I want to approximate this summation fi by this integral 0 to infinity f of x dx plus half f of 0. I want to substitute the summation as just this. So uh, I have to choose the value of alpha such that the remainder part, the r, is equal to 1% of the answer obtained by this. I will obtain some answer from this and I want r to be just 1% of this answer. That is what I want to ensure. Okay, so let's do this. What is the actual answer firstly? So the left hand side, let's actually evaluate the left hand side. I is equal to 0 to infinity e raised to power minus alpha uh, x. When I'm writing f of I, this is just simply alpha into I, right? Where I goes from 0 to infinity. We're replacing I by x only. Yeah, so this is equal to e raised to power I starts from 0. So it's 1 plus e raised to power minus alpha plus e raised to power minus 2 alpha plus so on, which is a geometric progression of infinite length. So what is the summation is simply a by 1 minus r, 1 by 1 minus e raised to power minus alpha. This is the actual value of the summation. Okay, now what they're saying is let's try to approximate this with the right hand side. So f of x we know is equal to e raised to power minus alpha x, where x is greater than 0, so I don't need to put the modulus sign there. Integral of this is e raised to power minus alpha x dx from 0 to infinity is equal to e raised to power minus alpha x minus of alpha 0 to infinity. At infinity, because alpha is greater than 0, at infinity the value will be 0. At 0, the value will be 1 by alpha. All right. And what is f of 0? f of f of 0 is just 1. So half into f of 0 is just 1 by 2. So the right hand side is basically half plus 1 by alpha. This is the approximation. And the error is, firstly I have to calculate f prime of x. What is f prime of x? Minus alpha e raised to power minus alpha x. F prime of 0 is equal to minus alpha. 1 by 12 into f prime 0 is equal to minus alpha by 12. This is my error. So error is generally a modulus, right? And you have a minus sign also anyway. So r is equal to alpha by 12. What we want is that this error has to be equal to 1% of the approximate answer. So alpha by 12 divided by 1 by 2 plus 1 by alpha into 100 has to be equal to 1. This will give me alpha. So 100 alpha by 12 is equal to 1 by 2 plus 1 by alpha. So 100 alpha is equal to 6 plus 12 by alpha. 100 alpha square minus 6 alpha minus 12 is equal to 0. Alpha is equal to minus b, which is 6 plus minus square root of 36 plus 4ac. So 400 into 12, 4800 divided by 200. We know that alpha is positive, so the negative sign while solution goes away. I have only positive sign. 6 plus this. So all I have to do is just evaluate this. I'll just use my phone to evaluate this value. Square root of 4836 plus 6 divided by 200 gives me, so the value is 0.3777. etc. 0, 6, 7, something. Fine. So this is the value of alpha that I get. Here is the answer. Right? Great. Now the final one. I think it's been a long time. How much time has elapsed? Um, Acha, it's 1 hour 15 minutes. Okay, so I think we can take the next problem also. Okay, fourth one is the Legendre transform of the entropy function with respect to all three independent variables. That is internal energy traded for temperature, volume traded for pressure, and number of particles traded for chemical potential is. This you already know what is to be done here. Everything else will be with a minus sign. Only mu term will be with a plus sign. You know that you basically have to subtract the whole functions. So yeah, this was the answer, right? S minus I want u by t, even p by v, pv by t I want subtraction, but this one has to be positive. This is my answer. This is the Legendre transform. This is you have already done this. We used to do just Legendre transform with only one variable. Now they're asking for all three variables together. So you just have to include the others as well. So this is pretty straightforward. Nothing to be done here. Okay. So now let's try a different problem. Uh, okay, I have started solving this. Let's not follow the solution. Let's do our own, right? Okay, so now considering the kind of preparation you will require for an exam, we'll solve a few problems. This problems I have directly taken it from Kardar book, Meher and Kardar, which is a standard StatMech reference. I think it's also mentioned in Sir's reference list. So this is a very standard reference book, and I have taken a problem directly from that book. So let's try and solve this problem. We are talking about a generalized ideal gas here. Consider a gas of non-interacting identical spinless quantum particles with an energy spectrum given by this. Here what they are doing is generally we have energy k square by 2m. So let's forget this 2m or something. Basically its energy is k square. Now what they are saying here is that let's say that the energy has k raised to power s. The dimensions, like there is some constant here which will adjust the dimensions. We are ignoring the constant here. That's okay. The whole point is that the power of k is different. It is going to be k raised to power s. There's some different power here, and we have to solve using this different power. So now these are the kinds of particles. This is the energy spectrum contained in a box of volume v in d dimensions. So we are already given the energy spectrum. We don't have to speculate. So we generally did the 3D volume and the energy dispersion there. We don't need to do that. This is the energy dispersion which is given here. Calculate the grand potential and the density at a given chemical potential mu. These are the quantities to be calculated. Actually, we will not do this problem exactly as it's done here because we also can calculate the grand potential and everything. But uh, the thing is that we know better. We have some method. It's not that we know better, but there is certain method that we have used in the class, and we'll try to follow that method itself. I hope the recording is on. Yeah. So we'll try to follow that method itself. So what is that method? That method basically is, okay, let's read the further parts of the question. Find the ratio PV by E and compare it with the classical result obtained previously. Uh, Basically, they want you to calculate grand potential and these quantities so that you will be able to eventually calculate the quantities that they are trying to get further. But the thing is, the way we have learned it in class, we will not require to calculate grand potential for that. We'll be able to do it without that as well. So let's try to do that way. For fermions, calculate the dependence of E by N and P on the density at zero temperature. And for bosons, find the dimension below which there is no Bose condensation. Okay, so for the first part, what we want to do is mainly uh, write U, N, and PV in terms of the integrals that we had seen, right? This is what we want to do in the first place. For that, U is just simply integral over say I, epsilon I and I, right? N is just simply sum over Nn. And PV is something that we will see later. We know the method though. So now Ni is 1 divided by raised to power beta epsilon I minus mu plus Q, right? What are we using? Was it Q? I think it was Q. Niq. So Q is equal to minus 1 for boson and Q is equal to plus 1 for fermions. And we have to sum this over I. Now epsilon I is already given to us as k raised to power s. And sum over I is basically sum over k. So what we want to do is sum over k. K is just three-dimensional thing. 1 divided by e raised to power beta k raised to power s minus mu plus q. Oh, by the way, here they have mentioned d dimensions, even the dimensions they are taking as d. But the problem would be that in class we haven't exactly learned the solid angle in 1, 2, 3, in general d dimensions basically. We can evaluate it for 1 and 2 and 3 and all kinds of dimensions. But we haven't learned the generalized expression in class. And I don't want to go into the hassle of deriving it. So d I will assume as 3 only. The dimensions I will assume as 3 only, but you will see the dimensional impact. You will be able to make out that here the number 3 is coming because of d is equal to 3. And at least qualitatively, we'll be able to point out that if the dimension was something else, what would be the difference? Okay, so I'll initially assume as d is equal to 3 only, and I'll start the problem. I hope the motivation is clear. What we want to do is for this kind of an energy spectrum, I want to find this ratio PV by E, which comes out to be 2 by 3, right? Uh, yes, it comes out to be 2 by 3 in the classical case. We want to find it in the case when K, uh, the, the energy dispersion is K raised to power S. The energy dispersion is of this form. We want to find this ratio and we'll think about the other parts later. Let's first evaluate this. So for that, what I require is U and N I'm trying to write down in terms of the usual integral form that we had written. We had written an integral of this form, right? R is for 2 and divided by e raised to power r square plus q d cube r, something of this sort, if I remember. Maybe I am mistaken. Maybe d cube r wasn't there. No, no, it was there. It was there. I don't exactly remember. Basically, we had written an integral something of this form. Mm, and that is what we want to reduce this to now. Reduce this also to. This is my Ni. This is uh, sorry. This is capital N. When I take the summation, this is capital N. So this is also capital N. Now I want to write capital N in that form as well. Right. Okay. So let's do this. D is equal to 3 in my case. So I know the solid angle and everything. I know how to convert this summation to an integral. It will be V by 2 pi the whole cube integral 4 pi k square dk e raised to power beta e raised to power s minus mu plus q. Right. So now what further we'll be doing is firstly for fermions. Oh, by the way, so you might get confused that they have spoken about spinless quantum particles. Then why aren't we considering them as bosons only? Um, so the concept of fermion or a boson is just that for a fermion, the wave function is anti-symmetric uh, when we swap the position of particles, right? And for bosons, it's symmetric. Um, this property can also occur irrespective of the spin of the particles. You don't need a spin to do that exactly. But generally, like in nature, you require spin to do that. But you do find certain kinds of quasi particles, or we can still make the wave function follow the anti-commutation rules or the commutation rules corresponding to bosons and fermions, irrespective of the spins. That's what I'm trying to say. So here, when they have spoken of identical spinless quantum particles, but if you see in the question, they have also written up one part of the question for fermions, another part for bosons. So that gives you an indication that e- even though they are talking about spinless particles, we are still considering both fermions and bosons as well. So let's derive this for fermions and bosons both. So for fermions, we have n is equal to b by 2 pi the whole cube integral 4 pi. Let's take the 4 pi outside. We don't want to keep it inside. 4 pi mm, k square dk divided by e power beta ks minus mu plus q. E power beta mu is z, the fugacity as usual. Q is equal to plus 1 for fermions. And let's take beta k power s as some x. Then k is equal to x by beta power 1 by s. And dk is equal to 1 by s beta raised to power 1 by s x power 1 by s minus 1 dx. So now substituting this inside, n is equal to 4 pi v divided by 2 pi the whole cube integral k square. K square is just x power 2 by s divided by beta is power 2 by s into dk is 1 by s beta raised to power 1 by s x raised to power 1 by s minus 1 dx into the denominator z inverse e power x plus 1. So what we have is 4 pi v, and just simplify these constants, writing them again and again, v divided by 2 pi square, 4, 8, yeah, and 5, yes, integral x power 3 by s minus 1 dx divided by s beta raised to power 3 by s to z inverse e power x plus 1. This is what we end up with. Here you can see that x power 3 by s, beta power 3 by s. So qualitatively, obviously, with d being different, there would be a difference in these constants also. So that's why I always say qualitatively. So you can basically generalize this as qualitatively, this is something x power d by s minus 1 divided by s beta is to power d by s d by s z inverse e power x plus 1. dx. This is the integral that you end up with. So this is what I was trying to tell you. Uh, the whole, again, to mention the problem again, with dimension d, the general solid angle is something that you have to derive, and that derivation is something that I don't want to get into, which is why I just took 3 dimensions. Okay, but of course you can do this with a general dimension. That's the idea of the problem. You were supposed to do it with a general dimension. Okay, so anyway, this is my n. Now same thing I want to do with u, capital U. In that case, what I have is this exactly n only, but I also have epsilon I, right? Sum over I, epsilon I and I is U. So U becomes, this whole thing remains the same, just that I have beta, um no, I just have k power s, because epsilon I, what is epsilon I? Epsilon I is just k raised to power s, right? So I just have a k raised to power s extra, which would mean that I have, what would it mean? It would mean that x by beta is something that I'll have to multiply here in the equation of n. So v by 2 pi square x power 3 by s, because I multiplied this by x already, divided by s beta. Um, Hope I'm not making any mistake here. Or should I do it from scratch only? Epsilon is just k power s. K power s is, in those terms, it's just x by beta. So there is an evaluation that has taken place. So I think I can simply multiply with x by beta, and that should not be a problem. So beta is 3 by s plus 1. Yeah, dx on z inverse e power x plus 1. Yes, this is what I end up with. This is u. And now beta PV is also something that we had seen. Um, I don't remember the expression. I'll have to check the expression for beta PV. What? It had a log. This is what I remember. It had a log of 1 plus q. Okay, let's check the expression. I directly solved this, but I don't remember the expression part. This is beta PV is just this. Okay, I'll have to check it in Sir's lectures itself. So let me do that only. Hmm, hmm. So where was this? This was, suppose somewhere here. Actually, maybe not. Okay, no, not in this phase-space method. Not here. I think we had derived it here itself in the fourth lecture. Hmm. Here I remember, yes. There it was. Okay, here we had a final expression directly for P, but so we had it's not something I was hoping for actually. There was a more general expression. Okay, so beta PV, yes, maybe this was it. This was the expression for beta PV, right? Beta PV was simply, right, I was here. Hmm. So beta PV was Q sum over I, yeah, you have it right here. Log of 1 plus Q e raised to power minus beta epsilon I e raised to power beta mu. Yes, this is what I was looking for. Hmm. Okay, so to evaluate this, Q integral again, same thing. V by 8 pi cube, I'm directly writing it out. 4 pi k square dk log of 1 plus q e raised to power minus beta k power s square beta mu is equal to 4 pi qv divided by 2 pi square. Yeah, this k square dk, we know what it becomes. What does k square dk become? This is k square dk, right? Hmm. Yes, this is k square dk. So what does that become? Um, x power 3 by s minus 1, x raised to 3 by s minus 1 divided by s beta raised to power 3 by s into beta to the power 3 by s log of 1 plus q e raised to power minus x into z dx. So what we will do now is integration by parts, so that I get this also in a form similar to these guys. So that's what I'll try to do now. Integrate this by parts. Um, one more page. Yes. So integrating this by parts, what do we get is qv divided by 2 pi square. Um, I have to integrate this and I have to differentiate this. So firstly, I have to integrate this and keep this as it is. So x raised to power 3 pi s minus 1 plus 1, which is just x power 3 by s divided by 3 by s, so which is s by 3 into s beta raised to power 3 by s. S gets cancelled here. Sorry, this will be in a bracket log of 1 plus q raised to power minus x z, and this is from 0 to uh, x is k power s. Yeah, so 0 to infinity. It is b mod of k power s. So this is going to go from 0 to infinity minus integral of the same x has to be integrated again. So this remains the same 3 beta power 3 by s. Uh, but now you have to differentiate this and the integral will be there. So 1 upon 1 plus q e power minus x into z and derivative of this function as well. So which will give me q into z into e power minus x with a minus sign dx is what we end up with. Yeah, is equal to qv by 2 pi square. Uh, Firstly, I'll just write this integral and then I'll solve this term. X power 3 by s divided by 3 beta raised to power 3 by s. Um, I have a q outside and there is a q inside which gets cancelled with this term. With this term, I'm saying, by the way. So with the first term, the q gets cancelled. And z e power minus x, I'll take it to the denominator. So what I'll have is 1 divided by, I'll actually take it out from the denominator. So what I'll have is plus q here and e power x z inverse, and the numerator has nothing else, just dx. Yeah, this is what the rearrangement looks like. This is what we end up with. Plus I have this term, same thing, qv by 2 pi square into x power 3 by s on 3 beta 3 by s log of 1 plus q e power minus x z. This is 0 to infinity. At x equal to 0, this becomes 0, so that is not a problem. But what happens at x equal to infinity? Firstly, q is plus 1 here. Yeah, uh, q is plus, yes, q is plus 1. So now we have to evaluate what happens at x equal to infinity. Okay, let's do this. I hope the recording is going on. Yes. Hmm. Okay. Okay, so what happens here is I just have to evaluate x equal to infinity. What happens? This is what I want to check. So we know that log of 1 plus x divided by x, limit x tends to 0 is equal to 1, right? So just to do that, um, what I'll do is multiply and divide this term by q e power minus x into z. Okay, so I'm evaluating just this term, so that's why I'll write qv by 2 pi square. These are just the constants. Integral s power x power 3 by s divided by 3 beta power 3 by s. I don't care about these constants right now. Log of 1 plus q e power minus x into z divided by q e power minus x into z q e power minus x z. If q is 1, I don't really need to write q again, but that's okay. I just written it down. So this would give me 1 because e power minus x, this is basically a very small quantity. So this is like x tends to 0. So this gives me 1. But there is e power minus x into x raised to 3 by s. So x raised to power any number into e raised to power minus x for x tending to infinity is equal to 0 always, right? Because e power minus x goes to 0 much faster. So what we can see is that this term will not contribute at all. The second term will not contribute and I will have only this term. So what I get is simply v by 2 pi square integral x or 3 by s divided by 3 beta power 3 by s dx by e power x z inverse plus q. This is my beta pv. Right. And what is u that I had already derived? Okay, let me check this again. I've already I already have a beta power 3 by s here. Mhm. So what's bothering me is okay. Okay, let's see. Mm, yeah, actually, that is what I want. What I'm getting is correct, actually. Yeah. So this is beta PV, and let's see what is mu. Mm, not mu. What I'm checking is u. Copy. Yeah. So comparing these two, what we come to know is that beta PV divided by u is equal to these integrals completely get cancelled. These constants also get cancelled, most of the constants. But beta PV has 1 by 3 and u has an s, so there will be an s by 3, and beta PV has, yeah, so there will be one beta which will come extra, which is what we expect. So the beta gets cancelled here and everything else remains the same. So what is PV? PV is just s by 3 into u. Here 3 obviously is coming from the dimension d. So PV is actually s by d into u. Is this what we expect? Classically, S is equal to 2, D is equal to 3. Therefore, PV is equal to 2 by 3U. So yeah, it does match classically. And this is what we expect. So this was just part 2 of the question. We did not go through part 1. We directly jumped to part 2 because we can do it without part 1. Now, For fermions, calculate the dependence of E by N and P on the density N at zero temperature. Okay, for fermions E by N. Okay, dependence on density. How do we do that? Um, yeah, I think this can be done very easily. Um, because we're talking particularly about uh, zero temperature. We did not talk about low temperatures or something. We're talking about zero temperature exactly. So when T is equal to zero, we have beta is equal to what? Beta is tending to infinity, right? Beta tends to infinity. So in that case, mm, these integrals, we have x raised to power 3 by s. We may have minus 1 or not. Let's keep this in the bracket. Divided by e power x z inverse uh, plus q. For fermions, q is 1. So plus 1. This is the integral we want to evaluate. Uh, in the case of beta tending to infinity, e power beta mu, for a fermion, mu is something positive. So e power beta mu also tends to infinity, which is z tends to infinity, z inverse tends to 0. Z inverse is practically 0. So we don't have this term here at all. In the case of fermions, not for bosons. Bosons, there will be something different to do. So this integral will be very easily evaluated. First, let's calculate n only. Capital N, what will that come out to be? This is the expression we derived. Right. So because now Z inverse is 0, so this term will not play any part. By the way, this for low temperature, we'll obviously have to expand. So these kinds of calculations have been done in class. It is exactly similar to that only. You had d cube r divided by z inverse e power r square plus 1. You had something of this sort, and there was an expansion in z that was carried out in class. So you will have to follow exactly that if this was something about low temperature. But here for zero temperature, you don't need to do that. For zero temperature, I can simply set this term 0 and evaluate this. So v by 2 pi square uh, into s beta power 3 by s, something I'll keep outside. Mm, this integral will evaluate to what? This is just integral x power 3 by s minus 1 dx. This is v upon 2s beta power 3 by 2 pi square. 3 by s, it's not 3 by 2, sorry. 3 by s pi square into x raised to 3 by s into s by 3. This integral from what? What value to what value? This 0 to, is it 0 to infinity? Then in that case, Hmm. Right. So obviously you have to keep that in mind that this goes from 0 to kf only. Otherwise, this reverse sign. Obviously, you have e power x also in the denominator. Okay, that was a stupid mistake that I made. Really sorry. So how you have to look at this is z inverse e power x is e power beta ks minus mu. That's what we have, right? Yeah. So till the time k power s is greater than mu, you have the denominator, this term goes to 0. When ks is greater than mu, z inverse e power x is equal to 0. When k power s is less than mu, am I doing it? Am I saying something opposite? Yeah, when it's greater than mu, in that case, 1 by z inverse e power x plus 1 is equal to 0. But when ks is less than mu, then what I have is z inverse e power x is equal to 0. Right. So uh, k power s is equal to mu implies kf. Basically, k is equal to kf at that value. That is what I'm claiming. So this integral also goes from 0 to kf only. That is a that's a big mistake that I made. So n is simply v divided by s 2s pi square beta power 3 by s. This integral, as I said, goes from 0 to kf only. And the same thing, x power 3 by s minus 1. So it's just x power 3 by s divided by 3s. So s gets cancelled. Just 0 to kf. So what we have is, yeah. So we have v divided by 2 pi square beta power 3 by s 3 into, actually there is a 3 also inside, and I have kf power kf cube, yes, into beta power 3 by s here also. So this also gets cancelled. What I have is vkf cube divided by 6 pi square is equal to capital N. So N remains the same because the dimension is the same. Here there is a dimensional play, of course, which is why you get this 3 and all. But it won't be as simple as just replace this 3 by 2 and you'll get n for two dimensions. So let's not do that. U is equal to what? So by the way, this is rho is equal to just kf cube by 6 pi square. So now what I'll do is I'll try to write everything in terms of kf only. Right. So what is u? U is this expression. This is u. And again, the integral is going to be similar. V by 2 pi square. I have s and beta power 3 by s plus 1. Um, x power 3 by s plus 1 divided by 3 plus s divided by s, 0 to beta kf power s. So beta gets cancelled again. Uh, Here s gets cancelled, but there is s here. V divided by 2 pi square, beta gets cancelled, kf cube into kf power s, 3 plus s, right? Kf power 3 plus s divided by 3 plus s is equal to u. By the way, what is the question? What do we want to evaluate exactly? Performance calculate the dependence of E by N and P on the density. E by N and P on the density. Okay. So E by N density now we can clearly talk about here. Hmm. So what does it come out to be? Actually, there is 3 plus s here. Okay. So this dependence basically is a 6 pi square rho, so 1 by 3 is equal to kf. So kf for 3 by s would mean v by 2 pi square into 3 plus s into 6 pi square rho over 1 by 3. So 1 plus s by 3 is equal to u. We want u by n, right? So u by n, which gives me an n here also. So I get uh, 1 by rho here. So the overall density dependence comes out to be 6 pi square raised to power 3 plus s by 3 rho power s by 3 divided by 3 plus s into 2 pi square. Rho power s by 3. This is most likely going to be rho power s by d itself for a general dimension, but I would prefer not to speculate. And we want the pressure dependence also. Okay, so what was the expression for pressure? We had evaluated it simpler form here. Yes, here it is. Okay. So beta PV itself had a V, so obviously I can remove V and V from both sides. So V1. Um, let's evaluate and see. Beta P is equal to 1 by 2 pi square integral. You also have basically 6 pi square beta power 3 by s. X power 3 by s plus 1 divided by, yes, this is what you end up with, right? Um, and here what I'll have is x is basically 1 xf from 6 pi square beta raised to power 3 by s, beta raised to power 3 by s plus 1 kf raised to power uh, 3 plus s. Yes, it will be 3 plus s again into s divided by s plus 3. This is beta p. So what I have is just these betas get cancelled. I just have to put in kf now. What is kf? Kf raised to 3 plus s. What's this only? So it's just 1 by 6 pi square into 6 pi square rho 3 plus s on s plus 3 is equal to p. So basically, p is directly proportional to rho power 3 plus s is the idea. U is directly proportional to rho power s by 3. So these are your answers for the third question. I did not have to do a low temperature expansion. It would have it would have been feasible, but it would have been a little bit tedious. So because it's just zero temperature, I don't need to think about it. Now, this thing for bosons, find the dimension dl of S below which there is no Bose condensation. Huh. Okay. So for this part, the logic is going to be simple. Let's see where we have prepared a good expression for n. Yes, this is the expression, right? Here we have the expression for n. Okay, so this problem requires some conceptual thinking. Um, okay, why I'll tell you. So here what we are doing is perform this integration simply from 0 to infinity, right? Um, the thing is that at the value 0, um, basically when you're doing an integration, the limit here, because it's going from 0 to infinity, the limit of x will always be 0 plus, right? But at 0, exactly at x equal to 0, uh, you have some divergence. So exactly how this works out is that um, your n is basically split into n0, where basically x is equal to 0. Um, is x equal to 0 exactly? Let's think. We have basically it's we talk about zero energy. So it's just a moment. So what you have is basically at the lowest value of energy at the ground state, the density or the number of particles at just that one state, which would basically an integration uh, would not even exactly start from that point. It is going to be starting a little bit above from that point. So now that's what you have to do. Your actual number of particles n has to be written like this. It has to be n0, where n0 is the number of particles, the sheer number of particles which are in the ground state, and rest of the particles here given by this expression are all in the excited state. S beta power 3 by s to z inverse e power x plus 1. All of these particles are in the excited state, and these are the particles in the ground state. Now, what they're asking is what is the condition for Bose-Einstein condensation? As in, what would the dimension, which we are not considering here, but what would be the value of S, the limiting value of S, for which Bose-Einstein condensation will take place? That's the question. So, so the idea here is that you have some number of particles, and this basically yields some value, this expression. Okay. The maximum value of this expression occurs at x is equal to 1. By the way, e power beta mu, sorry, what did I say? At z equal to 1, I meant z equal to 1. E power beta mu, which is z, in case of bosons, can take value between 0 and 1 only, right? You would know this. Sir has already mentioned this in class. Uh, and the interesting bit here is that this is -1 for a boson, my bad. And the interesting part here is that this function, x power 3 by s minus 1 divided by s beta is to power 3 by s. This is just a constant, but z inverse e power x minus 1. This is a monotonically increasing function. This integral basically. It's a monotonically increasing function of z. If I'm calling this as some f of z, then this is a monotonically increasing function of z. Can we check that? Let's try and do that. Um, z x power 3 by s minus 1 divided by e power x minus z d by dz. Let's take a derivative of this. So what I'll get is x power 3 by s minus 1 divided by power x minus z minus z x power 3 by s minus 1 power x minus z the whole square into minus 1. Mm, so here z we already know is between 0 and 1 strictly, and k power s is greater than 0. So e power x is always greater than 1, right? Greater than or equal to 1, because ks is greater than or equal to 0. So e power x is always greater than or equal to 1. So this first term is always positive. Similarly, second term is always positive. So this is strictly increasing. So basically that's the point, that this function is always increasing. It's monotonically increasing for z. I took the derivative with respect to z. So for z, this is a monotonically increasing function. So in that case, the maximum value will occur at z equal to 1, because that's where it can reach, right? Otherwise, it will have lower values. So now the point is that this function, as we proved, is a monotonically increasing function. At z equal to 1, it will have its maximum value. So say I substitute z equal to 1, then this integral is just a constant. Okay. Um, Now think that the number of particles that I have, capital N, is less than this integral, is less than the value of this integral. Then I will have some other value of z, or some other value of mu, which will satisfy this equation, and basically I'll have a good distribution of all the particles. The point is, when the value of my capital N starts increasing, so that the number that I get from this integration is lesser than the total value of n. I hope the point is clear. What I'm trying to say is that the maximum value of this function that I've boxed here, this function, is at z equal to 1. Now, when the value of this function at z equal to 1, if the number of particles that I have is greater than that value, in that case, I would have a lot of particles which basically cannot be accommodated by this function, basically in the excited states, and they will all settle down in n0, which is the ground state. So that is the condition for Bose-Einstein condensation, that if this boxed function again, if this boxed function is giving me some finite value, if this integration is giving me some finite value, then I can just keep on increasing the number capital N, and at some value I will be able to achieve a condensation. But if this boxed function, this integration is diverging, then there can be no value of the number of particles at which I will be able to attain Bose-Einstein condensation. So the whole condition ends up at this problem, that this integral has to be a convergent integral. It should not diverge at z equal to 1. And because it's maximum at z equal to 1, I can just check at z equal to 1. At z equal to 1, I don't want this integral or this function to diverge. I want it to converge. I want it to be convergent. That's the whole point. Just ensuring that would mean that just ensuring that would mean that Bose-Einstein condensation can happen. Okay, so let's study this function. I hope you did understand this argument. I don't need s and beta and all. I'm taking z equal to 1. So this is e power x minus 1 dx. Where will this attain its maximum value? I am taking z equal to 1. So this function already is at its maximum. Uh, there is a possibility of this diverging at x equal to 0, because there is a pole here, basically very close to x equal to 0. So otherwise it would seem that for all other values of x, this will be a convergent thing. This function is going to be something finite and it will converge. At x tending to really large numbers, this will tend to 0. So that won't be a problem. Only at very small values of this function can it diverge. And that's what we are afraid of. That at close to 0, we are hoping that this does not diverge. Okay, so let's check that. Limit x tends to 0, x power 3 by s minus 1 divided by e power x minus 1. What is this limit? We can just simply evaluate this limit as 3 uh, by s minus 1, x raised to power 3 by s minus 2 divided by e power x. So now this is just 1. What we want is, wait, have I made some mistake here? This is a 0 by 0 form, right? So I can use L'Hopital rule, whatever that's called. Hmm, Integral, wait, I think I made some mistake. This integral is what I require convergence on. I want basically this integral near x equal to 0 to converge. 0 to say some epsilon. This limit will be from 0 to epsilon. In that case, Okay, no, actually, what I should be doing is this. This is a bad idea to use L'Hopital rule. Okay, so going again, what I try to say is the whole check ends up at this point that I want this integral to have a convergent value, not a divergent value, at near x equal to 0. That's it. That was the whole condition that we came up with. So let's check doing this integration near x equal to 0 only. So x is for 3 by s minus 1 divided by e power x minus 1 dx. So e power x, because x is very small, I can expand it at 1 plus x. So what I end up with is x raised to power 3 by s minus 2 till dx 0 to some epsilon. So if 3 by s minus 2, I want this to be greater than or equal to, no, just simply greater than minus 1, right? I want this to be greater than minus 1. If this is not greater than minus 1, in that case, I might have say x raised to power minus 1 dx 0 to x, and I would end up with log x where I have 0 here, 0 to epsilon, sorry, and I have a 0 here, which is divergent, of course. And anything lesser than that also, x power minus 2, which will give me minus 2 x power minus 1. No, it just give me minus 1 x power minus 1. Minus 1 x power minus 1, and even in that case, this is divergent. So I want 3 by s minus 2 has to be greater than minus 1 so that this integral does not diverge. A very simple condition. So basically 3 by s is greater than 1. 3 is greater than s. Mostly this would end up as d greater than s is the only condition that you have for Bose-Einstein condensation to occur. So d has to be greater than s. So basically in three dimensions, because 3 is greater than 2, where in we generally take s equal to 2. In that case, Bose-Einstein condensation occurs, which is what our practical experience is. But so that is what we found out. The dimension is basically dimension has to be greater than s. Is there condensation for s equal to 2 at d equal to 2? In two dimensions, for s equal to 2, basically a dispersion like k square, there won't be a Bose-Einstein condensation because we require d to be greater than s, but here d is equal to s. So using this condition, we know that in two dimensions, there won't be any Bose-Einstein condensation for s equal to 2 for the quadratic dispersion that we use. So just let me go through this argument again quickly, if at all you missed it out. Uh, I also myself found this argument a little bit difficult to digest. That's why I'm repeating it. So the idea is that at um, basically at close to 0 for z equal to 1 and x very close to 0, what we see is the divergence in the number of particles in the ground state, and that is what is Bose-Einstein condensation. When does that happen? That happens when basically you generally get the total number of particles by this expression only, and near x equal to 0, exactly at x equal to 0, you don't have any divergence normally. That's the normal scenario. But now if you have divergence, when will there be more particles in the ground state? When will Bose-Einstein condensation happen? When this term here will not be able to accommodate the number of particles that you're putting in the system. Okay, so basically at z equal to 1, which is the highest value of this term, when I substitute z equal to 1, I will be able to evaluate this function to some constant number when I put z equal to 1. And now once I do that, once I evaluate this number, if I push in more number of particles greater than the number that we have evaluated here, then obviously the remainder particles have to settle down at the ground state, which we will not be able to calculate using this boxed function because the integral is going from 0 to some infinity, and it is slightly above 0 that the integration starts, right? The limit is 0 plus. So it exactly does not calculate the number of particles exactly at x equal to 0. So that is why we have to separate this out. And the condensation will happen only when this boxed function is not able to take in all the particles. So now, when can that condition be satisfied? Anytime when this boxed function is not divergent for z equal to 1, in that case, this condition can be satisfied. Because if it's not divergent, basically this right hand side number converges to some value, I can simply put in more number of particles, increase the particle density, and get condensation. So all we have to do to check whether Bose-Einstein condensation can happen or not is to check whether this integral yields a convergent value uh, when z equal to 1. So all we want to do is we want to check whether this converges or not. Once we check that this converges, then we are sorted. Then we can be assured that Bose-Einstein condensation happens. So that's what we did. We tried to check the convergence of this integral, and we saw that the major problem will lie at x equal to 0, at x close to 0 only. So that's why we checked only at x close to 0, and we found the condition for Bose-Einstein condensation. Okay, so next time I will come up with another problem, hopefully two problems. I don't know, this takes a lot of time. Hopefully I'll come up with another more two problems, and we'll try to gain some more idea as to how to solve these problems. So I personally find stat work very interesting uh, because there are a lot of thinking and understanding involved in solving. This is a lot of algebra also, which is I think the part which initially a graduate student or undergrad student fears the most. But once you go through the algebra, then you can actually appreciate the beauty of this subject. So that's why we'll try and solve more problems if possible. And all right, thank you, and we'll meet next time. Bye.